So we have a tutorial now on interactive and embedded systems by Omar Attia from Apple. So let me introduce our speaker. Omar is a senior research engineer at the machine learning group at Apple, where he works on developing embodied and interactive foundation models. He holds a master's degree in computer science from the University of Waterloo, Canada, and a bachelor's degree in computer and systems engineering from Alexandria University in Egypt. So please join me in welcoming Omar.
Okay, slide next and back.
Yes.
Okay, perfect. Cool. Assalamu alaikum. Good morning, everyone. Thank you, Ibrahim, for the intro, and thank you so much to the amazing MenaML and KAUST teams that made this event possible. Really seeing the dedication and growth of this community year over year is very inspiring and very reassuring that our community and our region is moving in the right direction, especially with the uncertain times that the world is living in right now. Also, it's always a pleasure to be back in Saudi Arabia. I lived here for almost 12 years. I went to the Saudi public schools. And so it's amazing to see how much progress happened over a very short few years, all while maintaining the same things that made the Saudi people great. So now, without further ado, my talk today will be about embodied and interactive foundation models. This is an AI domain that gained a lot of traction over the past few years. And it is my personal view that of all the AI domains and applications that we know of so far, this one specifically has the highest potential to change our physical day-to-day lives to the better or also for the worse. So the stakes are very high in my opinion. Let's get some acknowledgements and notes out of the way. All the opinions and statements made here today obviously represent only me. They do not represent Apple or any of my previous employers. All the material discussed today is public information, nothing secret or proprietary to Apple or any of my previous employers. I'd also like to acknowledge that LLMs and previously presented materials helped me a lot in preparing this presentation. So the presentation is not original work. It's basically an amalgamation of many such talks that happened before that you can find online. Okay, this is the agenda for our tutorial today. First, I'll start with some motivating examples, showing how embodied AI is already changing the world around us and impacting the economy. Next, we'll try to understand what we mean by embodied and interactive AI. So we'll try to define it more concretely in multiple ways, and hopefully we'll discuss these definitions and compare between them. And hopefully that will teach us a little bit more about them. We'll talk about some of the foundational concepts for embodied and interactive AI. Oh, yeah, sorry. Yeah, as I mentioned, we'll start with the motivation. We'll talk about the foundational concepts of embodied and interactive AI. We'll try to extrapolate a pattern or a theme from multiple papers and multiple interesting projects. And finally, we'll discuss some of the risks and ethical considerations that are especially important for embodied AI. As it may be clear from this agenda, the goal today is not really to go into too great of a detail or depth for any of these topics. My goal today is to really pique your interest and sort of cover as much as possible from this field. And I'll refer to many resources in my reference list at the end that I highly encourage everyone who's interested to actually give it a read. Okay. So let's start with this question. If we think about the economical and the real-life impact of the generative AI revolution that happened in the past few years, the first thing that will probably pop into your mind is applications like ChatGPT or Gemini. I'm sure everyone here has used one of these applications at least once, hopefully a lot more, whether you're writing code, trying to answer questions, or trying to even chat about whatever problem you're facing in life. These applications have been very foundational and sort of disrupting in the way that they hit the market. Basically, all of these applications are language-based and language-presented intelligence. So this is what we can describe ChatGPT and Gemini as. This can be shown here by how many, like the time it took for each of these applications, or for some of these applications, to hit the 100 million user milestone, which is usually a very important milestone if you're going to make a truly global product. So ChatGPT is one of the fastest products to ever hit 100 million users. It basically took ChatGPT almost 2 months to hit the 100 million user milestone, compared to Facebook, for example, that took almost 4.5 years. Other products like Netflix and Spotify have taken basically decades to hit the same 100 million user mark. On the other hand, as shown by many serious and detailed reports, the impact of these language models, like ChatGPT and Gemini, and generative AI in general, has not always resulted in real-life, lasting economical impact. I will show an example report here that's now famous, called a famous MIT report called the Gen AI Divide, that was published in 2025, basically saying that 95% of all generative AI pilots at corporations and companies are failing, and they are not being deployed long-term. Again, this is not some sort of journalist or someone who hates Gen AI. This is MIT sort of economical and policy teams are reporting on this. 95% of Gen AI deployments are very short-lived, and they're failing. Following from this, it's my personal belief at least, that the current and near-term impact, especially economical, of generative AI and AI in general, is not yet in language-based and language-presented AI, but rather it is in embodied AI and its applications. Let's take a more specific example. Let's think about the automotive industry. So in the automotive industry, right now, and that statistic is from 2023, we have more than 1 million robots that are being used every single day, every single hour, to produce the vehicles that we drive and ride in every day. And since that number is from 2023, we have reasons to believe that the real number now is significantly higher. And if you think that this is, oh, this must be like the classical robots that, you know, the robotic arms that are static, that are not very adaptive, you would also be increasingly wrong as time goes by. Companies like BMW have recently announced over the past couple of years that they started deploying humanoid robots to automate many tasks around their factories. So these are completely adaptive robots that can do many sort of non-standard tasks outside of the production pipeline in their factories. I would argue that the largest, most economically impactful AI deployments in the world right now are actually not chatbots. They're actually some form of embodied AI or interactive AI that has already hit the factories, that is already hitting our streets right now, and that will always increase from here on out for the next 10, 20 years. If we even look a little bit deeper, we see that only with all of this sort of numbers that I shared, this is only about 8% of all manufacturing in the US right now has any kind of robotics at all involved. That means there is still a gap of almost 92% that is yet to grow into, that robots will grow into over the coming years. This becomes especially important as the economical direction of the world goes from, you know, the expensive trained human labor, and companies basically try to phase that out with robotics in their manufacturing and in other applications. So with this motivation behind us, let's try to define what is embodied and interactive AI. I'll start with the first definition of embodied AI, or embodied intelligence. It's a very simple idea, and the idea is that having a body is required for general intelligence to emerge. For Arabic speakers in the audience, embodied can be translated roughly to mutajassim or mutajassid. So basically, it's the idea that the AI is not just some abstract thing, it actually has a connection to a body that acts in the physical world or in some environment. Similarly, I'll define interactive intelligence as the idea that intelligence is not isolated or static. It requires dynamic, context-sensitive interactions with environment over time. Now, we can also think about these two definitions in terms of questions that these fields or domains try to answer. For embodied AI or embodied intelligence, the questions that are interesting in that field are questions like, to what extent having a physical body is necessary rather than just useful for developing general intelligence? Can true intelligence exist without a body? This true intelligence expression that I'm using here, also known as today AGI. I'm sure all of you have heard this terminology nowadays. So can we really have AGI without having an existing body? And how does having a body affect intelligence in general? So these are some of the questions that embodied AI solves, or really sort of cares about. For interactive intelligence, and as I mentioned for the Arabic speakers, it might mean متفاعل أو تفاعلي. For these interactive intelligence sort of systems, we want to study if a system can be considered truly intelligent if it's processing only static data, or if it engages in real-time contingent interaction with the environment. What really constitutes intelligence here? And an important question also for intelligence is, this may be a little bit more philosophical, is that is intelligence fundamentally an isolated or a solitary process? Or does it always require an other to exist? And that other could be either the environment, could be other agents, it could be really sort of anything that really makes that intelligence show. So I saw this figure while I was preparing this tutorial, and I thought it could also show a different definition of embodied AI. So this is from a paper that I will cite repeatedly into my talk. I highly recommend reading it. It's cited as number 10. It's Pirlo et al. In my resource list. I highly recommend reading that. But this figure here gives us a new definition of embodied AI in the agent's age that we live in right now. So we basically see two circles. On the left side, we see the circle of classical robots. So these are the robots that might not be too adaptive. These are the things that you're likely to see in a factory or a manufacturing facility, for example, where you have the robotic arms, like the ones manufactured in Germany by the company called KUKA. I think that's sort of one of the most famous manufacturers. Or the warehouse movers that are being used by Amazon to serve all of our orders every day. And on the right side, we have the more recent agentic AI circle that includes a lot more adaptive systems. So these are where your ChatGPT lives and Claude Code, like the coding agents, live. And so in this context, embodied AI is sort of a mix or an intersection between these two circles, where you want classical robots or classical embodiments to become adaptive and to become more smart by integrating some of the techniques that agentic AI has shown. Notice here, one of the reasons I like this figure is the fact that it doesn't only have humanoid robots. It shows here having drones as one such embodiment. It also shows autonomous vehicles as one very important embodiment. I live in the US. I live in a primarily tech-focused city like Seattle. Seeing the rolling out of autonomous vehicles every day around me, the number of cars is increasing almost daily. In other cities like San Francisco, right now, it's basically a fact of life. You can order a Waymo. It can come and sort of pick you from anywhere to anywhere. This is not a dream anymore. This is not some kind of future sci-fi. This is happening today, and it's only going to increase from here multiple folds over the next 10 years. So the ideas that I discussed so far of embodiment and interactivity are not new ideas, of course. Like many subdomains in AI, embodied and interactive applications trace the root to cognitive science and psychology. So more concretely, through the work of many cognitive scientists, especially around the 80s and the 90s, this very important framework called the embodiment hypothesis was developed. The embodiment hypothesis can be stated in multiple ways, but the one I thought sort of most represent what I feel about it is that human intelligence and cognition isn't just this abstract process. Human cognition and intelligence is deeply rooted in and shaped by our bodies, our physical bodies, our sensory experiences, and the interactions with the physical environment around us. So this is basically, I would say, the theoretical or the psychological base that a lot of this embodied AI is based on. Note that this hypothesis might seem too obvious for us nowadays, that of course you need an environment to interact with to sort of train intelligent systems and to exhibit intelligence in the first place. But it wasn't really clear to everyone for all the time, or for forever, basically. For example, this is a screenshot from a Wikipedia article about another famous hypothesis for some time about AGI. What it takes to actually get AGI. And that hypothesis was called the physical symbol system hypothesis, or the symbolic hypothesis. In this hypothesis, some AI philosophers basically thought that a physical symbolic system is necessary and sufficient. So basically, symbolic systems is all you need to get AGI. So for a very long time, like, this hypothesis was not just widely accepted, and it's still, I think, as of this day, it's not widely accepted. And so it's important, I think, to see the different points of view on what it takes to get AGI and how they sort of compete with each other, and hopefully how they integrate with each other. So to reiterate, this embodied framework sees intelligence and knowledge as not these abstract entities or abstract concepts, but instead it grounds them in sensory, perceptual, and motor processes that are relevant to us as humans. We can also refer to human development as a primary example of this embodied framework. It's clear to anyone who's ever interacted with babies, human babies specifically, that babies learn how to deal with their bodies and their physical environment around them long before they learn anything about language or numbers or math of any kind. So they don't know numbers, they don't know letters, but they know how to move their bodies. They know how to reach out to something and grab it. They know how to put it in their mouths. So all of these behaviors are sort of explained by this embodiment framework. That embodiment seems to be like a more fundamental level to intelligence that then would allow for other kinds of intelligence to appear and to emerge. This is one of my favorite examples of sort of the embodiment hypothesis in action. Now, as a preface, I'll say this is more anecdotal and even like an extreme, maybe even a little bit of a silly example. And I'll summarize. You don't have to read all of this. This is a post from Terence Tao. For those who don't know Terence Tao, Terence Tao is one of the smartest humans that probably ever lived. He was a child prodigy. He received the Fields Medal, which is largely considered to be the Nobel Prize equivalent of mathematics. He's a professor of mathematics at UCLA, and he's largely considered to be one of the most influential and important mathematicians of our lifetime. So in this post, basically, Terence Tao explains how he was solving a very complicated geometry problem that ended up earning him the Booker Prize later on. The part that I circled in red is, I think, the part that is interesting here. That this geometry problem, in order for him to solve it, someone like Terence Tao found himself closing his eyes, imagining that he was the plane being rotated in this geometry problem, and rolled his physical body on the floor back and forth in order to sort of internalize the intuition of the problem. Now again, this is very anecdotal. It's also very embarrassing, as he admits in this post. You know, his aunt started laughing at him because he was at her house. But rather not, like, I feel like this actually captures a lot of what I mean about the embodiment being a fundamental part of our intelligence. Notice that he didn't solve the problem eventually by rolling on the floor. He was able to take these ideas and formalize it into language and formalize it into a formal proof to solve the problem. But it's more about how we humans sort of build our intuitions, and that then these intuitions can turn into a more concrete kind of intelligence that we call today language or math or any sort of other domain. Before we go into the methods section, this is basically the last set of key concepts, just to reiterate what we're going to need before we go into the methods section. So the first definition is the definition of embodiment, and we've defined it already in multiple ways. But basically, the terminology that I think is going to be relevant from now on is this embodiment is basically the shape and the degrees of freedom that the agent has. So for example, if your agent or if your model or if your sort of actor is a robotic arm, this robotic arm is usually controlled by a continuous vector that controls the magnitude and the direction of movement that you want the robot to enact. So that would be, in this case, the degree of freedom or the shape and so on. If your agent, for example, was a drone, the control parameters become different because now you have the controllers on each of the fans and so on and so forth. The other definition that already came up multiple times, but I think it's going to be very, very important to make concrete, which is the environment. The environment in this sort of world is anything that is outside of the agent, that the agent has no control over. So this is basically the surrounding of the agent. And in this surrounding, basically defines two things. It defines the state of the world, basically how the world is right now. So any variables that you care about are going to be captured in the state. And the other thing is the action space. Basically, what are the valid actions that your agent can take into this environment? And then another very important definition is basically what we call perception, which is in one way the connection really between the agent and its environment. So perception is the agent's ability to understand the environment in various ways. For example, we as humans, we perceive our environment in various ways. We can see, we can smell, we can hear our surrounding. And that immediately makes something very clear for these agents, is that multimodality is extremely important to any truly embodied AI. That you can't have a truly embodied AI if the agent can only sort of deal with a single modality. It actually needs to have multiple modalities in order to act in the physical world. Another kind of perception that is also important is what we call proprioception. So this is one of the first kinds of perceptions that babies develop, as I mentioned. So proprioception is basically the ability to perceive self-movement. So it's the idea that I know that I can move my hand to somewhere, grab something, and move it back to my mouth, for example. And this is something that I might have alluded to before when I mentioned interactive and embodied AI. But basically, for the rest of the talk, I will use embodied and interactive pretty interchangeably together, even though there is a slight difference. Embodied usually means there's a physical embodiment in place, so an actual physical system and a physical robot, while interactive can mean a system that is interactive but not necessarily has a physical presence. So something like a UI agent or an agent that acts on your behalf in a digital surface. Okay, so these are some of the most important embodied and interactive problems that are very well studied. There are hundreds of research papers about each of these topics. I'll go through them quickly. One of them, of course, is robotic manipulation. So basically the ability for us to make a robot move in such a way to achieve a certain task. So here, an example would be find an apple and put it away in the fridge. So you have a robotic arm and you have a tabletop environment that has a few objects. And you want to basically make the robot do something to these objects. And here you would find the action space defined as joint velocity control. Basically, as I mentioned, it becomes some kind of a continuous vector that controls the magnitude of the action and the direction of the action. Another problem is navigation. So you have some kind of a 3D space or 2D space, and your agent or robot moves in this area to achieve something. An example of this is your Roomba. If you have like the vacuum cleaner that moves around in the house and sort of does all the floor, that's an example of navigation. That it has to navigate around the stuff on the floor, around your fridge, around your couch, and make sure that it hits all the right spots. So this is basically navigation. Here you would see an action space like moving left, moving right, if it's like a 2D world. If it's a 3D world, you will have actions like jump and go up and down and stuff like that. Surprisingly, games are also very sort of relevant to this embodied and interactive world. And so you will find here applications like video games, or even non-necessarily video games, stuff like chess and Go, can also be very relevant and very, very well studied in the embodied and interactive community. And then finally, what we call UI control. So these are agents that are able to, or sort of domains where you want the action to happen on a digital surface. So book me an Uber trip on my phone, set an alarm for so-and-so. So before the current wave of foundation models and large language models and large language vision models, each of these problems was basically studied separately. And so you would have to train a specialized robotic manipulation model. This is where you would see work like QTOPT by Google in 2018, or work like Dactyl by OpenAI in 2018. You would have to train a specialized navigation model. This is where you would see stuff like DDPPO, or Active Neural Slam, 2020. You would have to train specialized video games or games models. So this is the similar like DeepQ learning or DeepQ networks in 2015, and the Alpha family of models that are a huge success by DeepMind. So you have AlphaStar, AlphaGo, AlphaZero for chess and Go and so on. And then finally, you would have to train also a specialized UI agent. This is where you'd see models like DOMNet or papers like DOMNet and Pix2Act. The internal details of each of these models don't really matter, and we're not going to really spend time on sort of studying each of these. These are just examples that I think are relevant for us. And it's mostly important because we want to contrast it to how embodied and interactive AI is being done nowadays, is that we're not really training separate models anymore for these tasks. What we're doing is that we're using all of these tasks together to train a single generalist embodied agent across all of these tasks together. We basically want a single agent that can control a robot, can navigate a space, can play video games, and can control a device on our behalf. And the hope here is that the generalist agent can leverage the overlapping information across these different domains. So, for example, you need physical reasoning to do something like robotic manipulation or navigation. So there's a lot of repeated information that hopefully the model can reuse there. You can also need something like long horizon planning, which oftentimes shows very naturally in games and UI control. So hopefully if you can merge both of these together, you basically can get an even better embodied agent. So this is basically the majority of our time we'll spend on this sort of style of architectures. So this is the most common internal architecture for the modern generalist embodied and interactive agents. Let's try to break it down. We have in the bottom left corner, we have some kind of a text task instruction that encodes the goal that we want to achieve. So something like control the robot to pick up the apple, disable the 11:30 alarm, move past the obstacle, whatever really sort of piece of text that would encapsulate the goal that we want. And then we also oftentimes have the case of a visual observation. So that's basically an image that encodes the state of the environment at the time that the agent is interacting with it. In the case of a robot, this can be like an egocentric camera, so a camera that's basically mounted on top of the robot like a GoPro so that it can see its environment. In the case of video games and UI, this just becomes a screenshot of the data that we're dealing with, and that is fed directly into the model. So that's the bottom side. The core part of this, the most important computational part here, is the multimodal LLM, or the MLLM. So the multimodal LLM is basically the main component that does all the reasoning and computation here. And a multimodal LLM, for those who might not be familiar with it, is basically just like a regular LLM. The only difference is that it can actually handle text, it can handle images, potentially other modalities as well. And so as a reminder for everyone how LLMs work, so LLMs accept in feature vectors that represent token embeddings and process these embeddings in a certain way and then output on the side, as the output like these, another set of feature vectors that represent output tokens. The only real difference for multimodal LLMs is that these input feature vectors are not only textual embeddings, they can be embeddings of images as well. And so the model is trained to account for the relationships across image parts or image sections, basically. And so really the connection between the first part that I mentioned, which is the input, and the second part that I mentioned, which is the computational side, is this visual encoder component. And the visual encoder component is really just the translation layer between a visual observation into the multimodal LLM. So if you've ever used models like CLIP, like SIGLIP, or like DynoV2, these are all examples of such visual encoders, or models that can be used as visual encoders, where it basically takes in an RGB image, like literally raw pixels, and it outputs a set of vectors that can then be used as tokens instead of that image while you feed it to the multimodal LLM. Cool, so now we have figured out the input part. The output part is where really becomes very important to the embodied applications. Everything I explained so far on this is just multimodal LLM, nothing special here. The real part that really makes it or breaks it for embodied applications is this action detokenizer. So the output of the LLM, in the case of embodied applications, is not treated directly as language. So in regular LLMs, we take that output and we decode it into text tokens immediately. In the case of embodied multimodal LLMs, or the embodied applications for multimodal LLMs, the output of these models is almost always interpreted as some kind of an action vector that the agent will then take and apply to the environment. So it entirely depends on what environment we're in. This is where the embodied part or the interactive part kicks in. It really matters what environment you're in so that you can translate these outputs of the multimodal LLM to the right domain. So for example, if you have like a video game or UI control, we're lucky enough that most of the actions there can actually be encoded as regular language. So you can encode stuff like jump, move left, move right. You can actually encode those as textual information and train the model to actually output text as well in the output. And so it becomes very easy. It just becomes like a regular language decoding. Now for other applications like maybe robotic manipulation, this is not the case because the output that the environment is expecting is basically a continuous vector. In which case, we have to have a special kind of action detokenizer that takes that vector from the LLM, or from the multimodal LLM, and sort of modifies that into another continuous vector that then can be used by the environment. And so we'll talk a little bit more later about the action detokenizer if we have time. Okay. So to summarize, the multimodal LLM that will act as an embodied agent needs to accept a sequence of observations or actions. These observations can be textual or visual. They need to produce actions for different domains, and these actions are then processed further with an action detokenizer to actually customize it to the right environment. And then finally, all of this has to be initialized from a strong multimodal LLM. So we're not going to teach the model to be multimodal nowadays. We just take a multimodal model that is already trained for the multimodal operations, and we customize it for the embodied applications that we care about. This is a slide that I added just in case someone was more curious about the continuous action control case that I mentioned. I'm not going to spend too much time on this unless someone really feels the need to. But basically, these are 3 such algorithms where we can use the output of the LLM to make it respond, or to make it to customize the output of the LLM to a robotic vector, to a robotic control vector. So we can just add an MLP or a multi-layer perceptron, basically a linear projection on top of the output of the LLM, and that gets us basically the dx, dy, dz, which is basically the direction and magnitude of action. We can use something, basically uniform tokenization, where we discretize each action basically for each dimension. This is where like some of the work that we're going to discuss, like OpenVLA, does exactly this. And then we can also use something called residual VQ, or vector quantization. This is basically, this uses like a variational autoencoder to basically sort of compress the encodings into sort of discrete vectors that can then be used like regular tokens. So again, the idea here is not to get into too many of the details here. The idea is very simple. Based on the exact environment that you're in, you will need to customize the output of the LLM to hit the environment correctly. You can't tell the robot to move left and right. That's not how robots are going to perceive your action. You have to give them the exact vector that you want them to move to or move with. Okay, so these are some concrete examples for such embodied interactive agents that I think are going to be very relevant. Again, the goal here is not to dive too deep into what this particular paper showed. I'm going to show actually 3 such papers, and the hope here is to show you that all of them more or less follow the same architecture. So I want you to focus here in the middle, where you have a large language. This is from the now very famous PaLM-E paper by Google. PaLM, for those who don't know, was basically one of the first large language models that were built in the world. Google obviously was sort of very early in this space. And so PaLM-E is PaLM embodied. So they took the PaLM model, which is closed source, by the way. Like anyone outside of Google doesn't know how that was trained largely. And you'll see here that it basically has the PaLM language model in the middle. And then these are all sorts of tasks that were used to train the PaLM embodied, and the PaLM embodied model. So you have visual question answering. You'll have mobile manipulation, that they actually collected a bunch of data from robots for this. So this is, again, one of the things that Google does better than anyone. They actually have real robots that they can collect data from. They also trained on language-only tasks, tabletop manipulation, and task and motion planning. So they collected data for all of these domains, and they fine-tuned their closed source PaLM model to actually act across all of these tasks. Another example, and again, from Google, again, the details don't really matter. What matters is really the core part in the middle to show you that this architecture is basically repeated again and again in all sorts of papers. This is from the RT2 paper, also by Google, as I mentioned. You will notice here that RT2 has the vision language action model. This is sort of a new terminology that started appearing around that time. And the focus for RT2 was basically specifically robotic control. And so they took, again, one of the Palm models that they had, which is closed source. They fine-tuned it across multiple tasks. And you'll start seeing here this action detokenize part in the very end, where you basically get the output here to be like real robotic actions. Again, this is another concrete example for the same architecture, which is OpenVLA. This was a very famous paper from Stanford. And the great thing about OpenVLA is that unlike the other sort of embodied agents that we had before, this one is completely open source. So they actually open sourced the model weights. They used Llama 2 as their backbone. So Llama 2 is an open source model. They used open source visual encoders like DinoV2 or DinoV2 and SIGLIP. And the model itself, the weights are completely open, and the data you could also sort of collect online. So they use something like OpenX, which is a collection of robotics and embodied data sets. And so OpenVLA, again, follows largely the same architecture that we described, again with the action detokenizer up the top. But the difference is this one is actually open source, and you can download it, you can use it, you can actually understand how they did it. Okay. So now that we understand the model architecture and we've seen sort of multiple examples for it, let's think about how these agents are actually trained in real life. So now we know what it looks like, how it's actually trained to do these things. For all the examples that I showed, PalmE, RT2, OpenVLA, and many others, all of these were basically trained via supervised fine-tuning on interactive data. So someone would go ahead and invest in creating massive data sets of robotic manipulation, of navigation, and so on. And then they would basically take a very strong model that they had originally, and they run SFT on top of that model, supervised fine-tuning. Very simple, very scalable. The only thing that is not really scalable here is the data component. And so you had to have someone like Google willing to invest millions of dollars to actually go ahead and buy robots and actually have them do tasks and collect the data from them. So as I mentioned, all three models that I explained are basically exactly trained in this way. You start with a pre-trained multimodal LLM. You supervised fine-tune on interactive data that you collected, and then you have a final agent. Now, especially in the past couple of years, we started seeing another pattern that was very popularized by papers like DeepSeek or like work on basically online and interactive RL, reinforcement learning, where we started seeing that the previous agents that were trained via SFT are now being used basically as base models that are then fine-tuned even further with online reinforcement learning. And so the first part is exactly the same. You take a strong multimodal LLM, you fine-tune, do supervised fine-tuning on interactive data that you collected somehow. And then the next stage is that you take the output of that step and you do further fine-tuning with online RL. It's not really called fine-tuning nowadays, but it's basically, you can call it even some sort of a post-training with online RL. And this is where we see some of the interactive models that did like this, like the paper from our group at Apple is what we call GEA, or the Generalist Embodied Agent. The reason is why, the reason why people do this and sort of why do we pay basically for that extra step is that the performance gain is very noticeable. It's very significant. This works really well in practice, as this figure shows from again, the GEA paper by our team at Apple. If you just take a pre-trained multimodal LLM and try to test it on an embodied task for like robotic control, you'll probably hit around 0%. Like the model is not going to be able to actually do much on its own. Once you do SFT, whether PalmE, RT2, OpenVLA, you'll probably be able to hit 57%, basically above 50% success rates for this embodied or for particularly robotic manipulation tasks. Once you hit the online RL phase and actually invest in activating that, you get a massive boost on top. So you go from something like 57% to like 83% success rates. So we know that this kind of environment works. We know that this kind of technique really works well in practice. Yeah. And when I say here online RL, it's really important to distinguish between online RL and offline RL. So offline RL is basically when you collect more data afterwards and just run more SFT basically, or run more classical offline RL. That's not really what I mean here. We actually mean real online RL on the environment, on policy changing. So online RL basically requires millions of interactions with environments in parallel. So to do it properly, you have to invest a lot of the infrastructure. which is really becomes the real bottleneck here. So for robotics, for example, you require either real robots, like Google did, or you require high-fidelity physical simulations software, and that becomes very computationally intensive. Applications like Mujoku, which is a physics engine, basically, helps in this kind of situation. For the case of UI, again, in order to run these online environments, you actually need to run thousands of virtual machines and collecting screenshots over the network. And so again, this can be very expensive very quickly in order to run these environments and simulators. This is the case for stuff like Android World and OS World. I'm not going to also spend too much time on this, but I thought it would be useful to share this abstraction with everyone who's interested in online RL. And this is not specific to embodied AI. This is actually specific to online RL specifically, is that we have this interface that's called the GIM interface that was developed by OpenAI. And that interface basically defines the interaction between the agent and the environment in two important functions. There's the reset function that basically resets the state of the environment and gives you back the state. And then you have the step function that takes in an action and gives you the state of the environment after such action. So this abstraction becomes very important if you're actually going to implement such environments. Now, the rest of the talk is really just maybe a couple more minutes. I'm going to follow up on the fantastic talk by Hadi Salman from yesterday, where he talked about, chain of thought prompting, like RL on chain, like the sort of DeepSeek style. And that's really one of the main benefits of using LLMs for embodied agents or for embodied tasks and interactive tasks, is that a lot of the techniques that actually worked to make LLMs better also work almost out of the box for the embodied applications as well. This is one such example, which is the reasoning or chain of thought. So chain of thought is obviously a proven method now to improve LLM performance across many tasks. I'm not going to dive too deep into it. Everyone here hopefully attended Hadi's talk yesterday. But the idea is very simple, that before you output the action from the LLM or from the agent, you actually have the agent output a plan first or output steps first that then is consumed by the agent before it generates the action. So that's shown here on the left-hand side, on the right-hand side. And as no surprise to anyone, embodied and interactive domains actually benefit from this as well. So work like embodied chain of thought, ECOT, embodied chain of thought, basically took the OpenVLA model that we just showed, and the only difference they did is they actually had it output chain of thought first, and then as an output, it basically got 28% more on the same benchmarks. This is another approach that Hadi talked about yesterday, so I'm also not going to spend too much time on it, but this idea here is popularized, like the reasoning via reinforcement learning has been popularized a lot by DeepSeek in their R1 release. And the summary here again is that instead of using prompting, like specific human-based prompting to get more chain of thought, to actually do the chain of thought via RL, via reinforcement learning directly, and using efficient reinforcement learning like GRPO to do that basically. This is still an active area of research, 2025 and 2026. We've already seen a couple of papers that started doing this. So we have Robot R1, which was, I think, accepted to NeurIPS last year, and Nav R1, which is doing the same for sort of navigation specifically applications. Now, this is the last slide, which is basically the risks and ethical considerations for embodied AI. Now, again, I highly recommend reading 10 and 21, so Pirlo et al., where this and the previous figure that I also mentioned come from. I highly recommend this to anyone who's interested in policy or in risks of AI in general. I think they're very well written and sort of very structured in this way. So that paper basically structured the possible risks for embodied AI under these 4 categories. One of them is what we call physical danger or physical risk. So this is very simple. Because these agents act in a real physical environment with people around them, they can actually induce very difficult and purposeful harm on the people around them. Thank you. So what is an example of this? An example of this is like, a self-driving car hitting a pedestrian, a drone strike to hurt or kill people, and obviously, robotic policing or robotic attacking agents. The other side is informational, so basically privacy concerns. Think of a world where drones basically screen everyone around you and monitor your every movement. There is an economical impact as well that we can't underestimate, which is labor displacement. Power concentration, those who already have the money will be able to buy such robots and have them go further to their own goals. And obviously social risks as well, like the lack of trust and transparency, unclear liability standards, like if a self-driving car hits someone, who's now to be blamed? Is it the actual car? Is it the algorithm? Is it the algorithm maker? We basically need a lot more guidance on this. Yeah, this will be all for me today. Thank you so much. This is a list of references and reading lists. I highly recommend reading those for anyone interested. Thank you very much.
Thank you, Omar, for the wonderful tutorial. It was really quite great. So before we open the floor for Q&As, I'll do a shameless advertising. If you are interested in this domain, we also have Polygema. You may want to consider it as another foundation model. I'm not biased, but it happens to be developed and released by our team. So yeah.
I spent half of my time talking about Google. I think they know.
Yeah, okay. And the other thing is, if you are also interested in this domain, we have a lab session tomorrow about VLMs and robotics. So hopefully that would help you also internalize some of these ideas. So yes, we have questions. Let's start with this one. Yeah, please.
Hello, thank you, Omar, for the interesting talk. I wanted to ask about world models like VJPA developed by Yann LeCun. How do you think they are placed in this type of embodied AI exactly, and the main difference from using a VLM and training it using RL?
I think VJPA style, world models are not necessarily VJPA. World models is basically, understanding the dynamics of the world. VJPA happens to be a modern, or like a sort of a recent technique that was suggested by Yann LeCun and others. Actually, it was suggested by many people before Yann LeCun. But the idea here is that it's still too early. Like there are not many people sort of working on these architectures just yet. Maybe, I expect that in 2026 and 2027, we'll see a lot more papers on how VJPA and the VJPA style papers can be used in the embodied settings. But as I mentioned, like there's many active areas of research in this field. And yeah, I definitely am not, I would say, married to the LLM or the VLM style of doing things. But yeah, it would be very interesting to see how these models evolve over the coming years.
Okay, thank you.
Thank you.
Hi, thank you for your presentation. I wanted to ask you about the current state-of-the-art accuracy and latency of using multimodal models on robots that are latency critical, like self-driving cars and conveyor belts, because robots at home have the advantage of waiting before and analyzing before performing a task. I know that Waymo uses sensors with cameras, but Tesla only uses cameras and neural nets. So I wanted to ask if this is posing any kind of danger currently, or we can rely on them immediately.
You will never hear me say rely on them immediately. I don't think, sort of, particularly for self-driving cars, I am definitely kind of biased to the way Waymo did things, because they really focus a lot on sensor fusion, and they have LiDAR, they have multiple points of, they don't have a single point of failure, basically, unlike Tesla's approach, which is more like camera only, so there's more sort of single point of failure concentration. I don't think we can rely on any of these applications just yet as they are right now. I think there is still plenty of room for improvement, and I think it's going to happen at a much faster pace than anyone can imagine. When it comes to the latency side of it, the latency, like you mentioned, not all applications are latency critical. If I want my robot to fold my laundry, I can wait a couple of hours. It doesn't really matter. But if I want the self-driving car to respond immediately to a pedestrian that jumped in on top of the street, then it needs to be very real time. So the latency perspective is very application dependent, and it's very critical, obviously. It's the difference between life or death in many of these situations.
Do you think convolution-based models are more reliable right now than multimodal models?
Do I think what, sorry?
Convolution-based models like YOLO?
Right now, I don't think there is enough people working on convolutional-based like embodied. I think everyone is sort of doing transformers right now because the foundation models using transformers are just so much stronger, and the scale characteristics of them are just so much better. So if you switch from an 8B model to an 80B model, there's going to be a very clear gap between them. For convolutional models, that's not clear. The scale is not well studied for these kinds of models as of now.
Thank you.
You're welcome.
Thank you for the talk. My question is about the at the term that you mentioned as a key concept, I think if I pronounce correctly, proprioception.
Proprioception,
So
yes.
yeah, do you think that emerges in these multimodal language models? And if not, can you speculate on how we can build models that can have that?
That's a great question, and I don't have an answer. Like, I don't know if you can train specifically for proprioception. I know for the case of robotics, people use proxies for proprioception as like extra sensors and so on like that, just to get, you know, where did the robot move from one point to another. So you basically keep a delta of how things moved from step time 1 to step time 2. But I don't know if we can train specifically for proprioception. Proprioception is not actually an AI terminology at all. It's a psychology and sort of child development terminology that we hope that our models will be able to capture as we train them on these spatial and, you know, 2D, 3D tasks. I don't know if that answered your question.
So like maybe as a follow-up question, so
So we're running out of time. If we could just,
I'll be around. Yeah, we can talk about this.
maybe you could just leave.
Oh, okay.
Can you give the opportunity just for another question? If you have a question,
You talked about different detokenizations for like the mappings between the text and the different environments. But I wanted to ask, is there any possibility in the future that the learning and the foundation models in similar embodiments within robotics can be transferable? So like between, let's say, a humanoid and a wheeled robot, is there a potential for the learning to be transferable from one foundation model to another?
I think that's already happening now. Like, because we train all of them together in the same base model, we have sort of data and reasons to believe that the model actually learns transfer between them. The real difference is basically at the interface layer or the output layer. The output layer needs to be actually dedicated to the environment because the action that you're going to apply to a car is different from the action that you're going to apply to a robot. You need to move the steering wheel, you need to press a certain pedal. These are different interactions. So the detokenizer is basically that component that connects whatever the LLM or the multimodal LLM learned to the output environment.
So the underlying representations are similar, is what you're saying?
The underlying representations are baked into the same model right now.
Okay, thank you so much.
Thank you. Thank you, everyone.
Okay, thank you again, Omar. So we're going to take a break for about, I don't know, 10 to